take it away.
All right. Hello, we're Operation Concentration. Our team is made up of Marcus, Stephen, Matthew, Kristen, Jenna, and Josh. Today, we will cover who we are, an overview of our design in each subsystem, and outline the analysis that we completed for each subsystem. First, I would like to cover who we are as a team. Our overall goal is to create a durable modular heliostat with 2 axes of rotation. We believe that we can design the best heliostat through our unique ability to produce creative solutions to the proposed problem. We are passionate about this project due to our desire to improve the renewable energy industry. Currently, many renewable energy products are cost prohibitive. Our design will provide a durable and lower cost heliostat that will allow companies to move forward with using solar energy and further promote the usage of clean energy. Our overall economic drive overlaps with why we are passionate about this product. We believe that our heliostat will be able to compete successfully in the current economic climate due to its lower cost and long lifetime. This price and lifetime will allow for the purchase of heliostats that cover entire solar fields. Overall, our team is confident that the design proposed will positively impact the renewable energy industry while proving to be a successful and innovative product. Our overall design was split into 4 subsystems: the mirror, the controller, the heliostat base, and the module base subsystem. The mirror subsystem is separated into 4 separate reflective surfaces made of borosilicate glass. The controller subsystem is based primarily on a rack and pinion system that uses 1 motor and a connecting rod. The connecting rod is able to control each mirror through connecting linkages. Next, the heliostat base subsystem uses a linkage system that rotates about the vertical axis due to the rotation of a circular plate in the module base powered by a separate motor. Each linkage rotates based on the force supplied by the connecting rod. Lastly, the module base supports the weight of all other subsystems as well as rotating about the horizontal axis to place each heliostat in the ideal position. It rotates using 1 motor and a Lazy Susan bearing. It also encloses the control panel, which holds an Arduino and ESP module. It is fastened to the ground using 4 concrete posts. Overall, our design uses 1 module that rotates about a central axis and a connecting rod with the ability to actuate all 4 mirrors together. This design was able to limit shading while also following the sun for maximum energy collection. Our product was designed to be as close to a square as possible to ensure that each mirror could rotate fully without hitting one another or shading. It had dimensions of 1 meter by 1.35 meters, which allows each module center to be spaced 1.7 meters from each other. This allows for enough spacing for people to walk in between each mirror during maintenance operations. Here's a quick overview of our separate subsystems. We will begin a more in-depth study of each with our mirror subsystem.
Each mirror is 1 meter by 1/4 meter, and they're all made out of borosilicate glass. The reason borosilicate glass was chosen was because it has lower stress concentrations from thermal expansion and contraction with the change in temperature. The mirror is held onto the backing with 4 mirror clips. Attached to the mirror backing are 2 V-shaped supports that are welded on and then bolted. There are welded tabs that are bolted to the V-shaped supports, and then there's also a linkage that is attached to a welded tab. All 4 of the parts other than the glass mirror are made out of zinc galvanized low carbon steel sheet metal. Here's our customer needs map for the mirror subsystem, and I'm going to highlight a few that we thought were most important. One of the ones we thought was most important was the collection area being around 1 meter squared. And to maximize the effectiveness of each heliostat, we chose a reflective area of exactly 1 meter squared. The next one, and probably the most important, was the ability to withstand the ambient and solar conditions of Las Vegas, Nevada. So this means being able to withstand the winds and temperature changes that are known in the desert. To help with this, we backed our mirror with sheet metal to prevent it from cracking under the high loads from the wind, and chose borosilicate glass to prevent it from cracking from the temperature changes. The last 2 needs that we thought were most important was the ability for the entire field to deliver 1 megawatt to the receiver target, and this was done by using 1,500 heliostats in an entire field. And we also had the need to provide the solar concentration of 1,000 suns. And this was done by having 1,500 heliostat assemblies, and also accurately tracking and reflecting the sunlight using our design that with the high control we were offered with our design. The first analysis that was done on the mirror was drag force calculation. This was arguably the most important analysis on the mirror because this was found to be the largest load any part of the entire heliostat system, not just the mirror, would experience. The reason that the drag force analysis was done on the mirrors was because they have the largest frontal area. The first assumption that was made for these analyses were that the mirrors were in the vertical position because this maximizes the frontal area and creates the largest coefficient of drag. This means that the mirror is perpendicular to the free fluid flow. At 90 degrees, the coefficient of drag was 1.98, and with a wind speed of 44.7 meters per second, the total force of drag on one mirror was 605.8 newtons. Using this force of drag, we then found the maximum bending force that the mirror would experience. That includes, the way this was done was by assuming the mirror acts as a simply supported beam with a distributed load across the face. The two parts that support the beam are what would be the supports of the mirror. Using a factor of safety of 2, the maximum force was twice that of the drag force, and this gave us a maximum bending force or stress of 359.44 megapascals. Another analysis we did on the mirror was the downforce. This also contributed to other forces that were used throughout the rest of the heliostat analyses. For this, we found the coefficient of lift for a rectangular plate, and we chose an angle of attack that was 15 degrees. Anything more than that would create flow separation. And generally, as you can see with the equation, the higher the angle, the more downforce or the more lift it'd create. But we weren't really interested in the lift, we were more interested in the downforce because this would work in conjunction with the weight. And so the way the lift works, or downforce, is just lift in the opposite direction, meaning the plate has a negative angle of attack. Using an angle of attack of 15 degrees, we had a coefficient of lift of 1.32, and this resulted in a downforce of negative 402.69 newtons using the same 44.7 meter per second winds. The last analysis done on the mirrors was the maximum shading. With our current geometry and the sun in the worst position, we had a maximum shading of 18.7%. But this isn't too bad because this only happens for a short period of the day. And because of the way our heliostat field is set up, not all of the mirrors will affect this amount of shading at the worst or in the worst time of day.
So this is our controller subsystem. It consists of a connecting rod driven by a 16.7 RPM Cytron motor, which pulls or pushes the leading edge of each mirror to its desired offset using metal linkages that are connected to the mirrors. The motor has an attached spur gear, which makes contact with the indented lower edge of the control rod that serves as a sort of rack and a rack and pinion system. So as the spur gear rotates in a given direction, it will force the control rod in that same direction. The range of motion is controlled by physical stoppers on either side of the indented portion of the control rod, as well as limit switches, which are activated by contact with the physical stoppers. And additionally, we also have 2 rod guides that were positioned along the length of the connecting rod to prevent the rod from bowing outward, which is a possibility given the ambient wind conditions in the Nevada region. There were additional design considerations we had to make based on the region's terrain. For example, to prevent ambient sand particles from having negative effects on the controller motor, we encased the motor in a polyethylene shield, and we also added brushes to where the casing meets the rack portion of the controller to prevent sand particles from embedding into the rack and then grinding into the connecting spur gear. This is the customer needs map for our controller subsystem. Based on the need to minimize tracking errors and cost while maximizing the reflective efficiency and operational lifetime, we decided to use sheet metal for our control surfaces and linearly actuate each mirror about a single axis with a single motor. The use of sheet metal helps improve the durability of the structure, which adds to the overall functional lifetime. and the use of a single motor for linear actuation helps compensate for the cost of sheet metal. So substituting a non-metal material for some of the control surfaces would have been cost effective, but ultimately our design would not have the actuation accuracy and factor of safety it currently has. Motor calculations were performed on the rack and pinion system with a full cycle of movement assumed to take about 600 seconds to perform. The force output of the rod was 1.369 times 10 to the negative 6 newtons, and the resulting motor torque was 1.739 times 10 to the negative 8 Newton per meter. This is because the cycle of movement happens so slowly that the necessary acceleration of the rod is about 1.398 times 10 to the negative 6 meters per second squared. So the minimum power to move the rod was therefore found to be about 5.265 times 10 to the negative 7 watts. A heat transfer analysis was also performed on the polyethylene casing of the controller motor to ensure that the motor surface and the neighboring limit switches wouldn't overheat. In this scenario, the casing was subjected to the relatively harsh ambient temperatures of the Nevada region. So it was assumed the casing was heated to about 50 degrees Celsius, and that air heated to 48 degrees Celsius would enter the enclosure through the rack opening. And after performing the heat transfer analysis with respect to the motor's mechanical work, its electrical power, and the heat leaving it, the surface temperature of the Cytron motor was found to be about 48.4 degrees Celsius. So we concluded that there was very low risk of the components overheating in the enclosure.
The next subsystem is the Heliostat base subsystem. So the picture on the right is our Heliostat base plate, and this piece is important because it connects the module base subsystem to the controller and mirror subsystem. So part of our design is that the entire Heliostat base plate rotates with the mirrors on top of it. So it was important that this piece did not fail. So the plate is made out of zinc galvanized low carbon steel sheet metal, and it's 1.33 by 0.545 meters. The edges are bent up by 15 millimeters in order to have more strength and durability. And then there's also cutouts in the base plate, and the metal from those cutouts are used for other parts. Here is a customer needs map for the Heliostat base system. So we use what the Heliostat base subsystem does is it uses innovation to reduce the heliostat size by having a smaller size than 1 meter. It allows enough space to fit 4 heliostats with minimal shading, as we showed before for the mirror subsystem. And then it also has a really low module base area to reflective area ratio. Okay, so the first Heliostat base subsystem analysis needed to be done so that we knew that there wasn't going to be failure, especially because there's cyclic loading caused by the wind forces. And the wind forces were calculated for the mirror subsystem. The original plan did not have 15 millimeter edges, like curved up edges, and it resulted in failure from wind loads. So it was recalculated with a new cross-sectional geometry. The first step was to calculate the moments, so the maximum minimum moment. The forces being applied that are red are from the mirror weights, and the green force is from the lift force and down force from fluid forces on the mirrors. The next step is to analyze the cross-section to get the necessary information. So the dimensions of the cross-section for the weakest point are above, and then it was split to 3 different areas in order for the centroid and second moment of inertia calculations. So those are the areas that we used. The centroid was found to be 3.066 millimeters. And then the second moment of inertia using the same areas was found to be 99,413 millimeters to the 4th. We can also use the centroid and the maximum distance from the centroid to find our maximum Y value, which we use in the bending stress equation. We found a maximum bending stress and a minimum bending stress. Using the maximum bending stress and minimum bending stress, we found a mean bending stress as well as an amplitude bending stress. Since it doesn't reflect perfectly around the time axis, an equivalent completely reversed bending stress was found to be 17.14 megapascals. Since the ultimate tensile strength is 635 megapascals, the endurance limit without correcting for Marin factors is found to be half of that at 317.5 megapascals. The two Marin factors that we thought most important were the surface factor as well as the shape factor. The surface factor is a function of the ultimate tensile strength, and the shape factor is dependent upon the equivalent diameter. We simplified the geometry conservatively to have an equivalent diameter, and that's the figure to the left. And that the Marin factors were found as 0.816 and 0.819. The final endurance limit after correcting for the Marin factors is 209.5 megapascals, which allows for factor safety for infinite life of 12.23, which is much better than before, which was failing at yielding. So curving up the edges was important. The heliostat-based subsystem also controlled how close we could space the heliostats and still have them not shade another module, and also allow for space to walk in between them, as Jenna was talking about earlier. So the closest distance that the two heliostats could be was 1.7 meters. And so what we envision for the whole field would be rows of heliostats that are located 1.7 meters away from each other, with every other row having 1.9 meters away from each other to allow space to walk.
Our fourth and final subsystem, but certainly not least, is our module-based subsystem. Our module-based subsystem features a module-based support, which houses all of the components attached to it, but also is responsible for holding up the weight of the heliostat baseplate and the mirror subassemblies above it. The module-based support houses the circular module base, which is the circular disc at the top, which is rotated by our 16.7 RPM motor. This circular disc is responsible for connecting the two subsystems, which provides that vertical rotation, or rotation about the vertical axis, for our heliostat base. The Lazy Susan, which has ball bearings in it, rotates and provides free movement and a 500-pound capacity, which is acceptable given the weight of our heliostat base. Additionally, around our module base support is a high-density polyethylene shielding case. This shielding case, you'll notice, has perforations at the top that are angled at 45 degrees, and this is to allow for the environment on the inside to maintain a cool temperature, since it houses many electronics, but also the shielding case is designed to keep out the ambient conditions, such as potential rain, sand flying in from wind, or even pests. Mounted to our shielding case is our control panel. It features an Arduino Uno, a 12-volt motor driver, and an ESP-W2 microcontroller, which has Wi-Fi capabilities. And then as far as mounting our module-based support into the ground, we have 4 concrete cylinders, which the legs from our module-based support will protrude into. So once the concrete is poured, the module can simply be inserted, and it is all prepared and ready to go to reflect sunlight. So a bit more in depth about the critical features of this subsystem. Beginning in the top left, we have a close-up of our Lazy Susan, our circular module baseplate, and our motor with an encoder. So you can see how the Lazy Susan bridges between the circular module baseplate and our module base support, and additionally how our motor, which is mounted to the same module base support, is able to rotate that. You'll notice the internal geometry of our base plate is similar to that of an internal gear, which will be water jet out. And that is how our spur gear is able to engage with it and provide that rotation. In the upper right-hand corner, is also another underneath view of the circular module base plate. And this time you'll notice a limit switch. So that limit switch tab is responsible for making contact with the limit switch, and in conjunction with the encoder, where this enables us to accurately locate the rotational position of our heliostats throughout the day through use of the limit switch tab, engaging with the limit switch and setting the home at the end and the beginning of each cycle. So that, like I said, we know where we are throughout the entire day. And then in the bottom is our control panel. Once again, to reiterate, we have the Arduino, we have a 12-volt motor driver, and our microcontroller. So a bit about how all these components work together to actuate our system. The microcontroller, since it has Wi-Fi capabilities, will receive information from the receiver tower and deliver it to each individual heliostat. Therefore, and from there, it is delivering these to the Arduino. The Arduino is able to then relay corrections for the two motors, whether it be speed, rotation, or position, to the motor driver. And the motor driver is responsible for powering the entire system. It receives 12 volts from the power grid, delivers it to each of the two motors, but also supplies a 5-volt power supply to the Arduino. A quick overview of our customer needs for the module base. You'll notice that this one's relatively small. That's because the majority of the other customer needs were satisfied through the other subsystems. But to quickly cover this, the top two go over costs of the overall system. And we tried to minimize the cost of this particular subsystem through bulk discounts, like in our sheet metal purchases, and also using the cheapest off-the-shelf parts that were the most reliable and effective for our purposes. The main and most important customer need for the module-based subsystem is to protect and support everything. So once again, here we have keeping out the sand and pests, and also protecting from any rain damage. For our module base, since it is supporting the entire system, the biggest concern was whether it would be able to do so. So on the left here, we have two forces, the force of gravity and the force of drag. You are looking at a side view of one of the module base legs. And on the right, we have a cross section, which is a top-down view of one of the legs. And you'll see it's similar to a 90-degree L shape. So taking that cross section into consideration, we can then start to look at the bending stress and normal stress. First here, we have the centroid, which is at 8.1, followed by the calculation for the second moment of inertia. On the next slide, we'll go into the bending stress, but at the bottom here, we also have the calculation for the normal stress, which is simply the force of gravity over the area of all the legs combined. So it is distributed. That comes out to about 2.2 MPa. And as I mentioned, now we're getting into the bending stress. The moment is calculated based on the drag force, which acts perpendicular to the leg. And that comes out to 15,000 newtons per millimeter, giving us a bending stress of 1.5 megapascals. And so now we can calculate our factor of safety based on the yield strength of our material, which is steel, and the two stresses, which comes out to a very large factor of safety of 136. However, while this factor of safety is very large, our previous design iteration had failed due to, instead of there being 2 legs on each of the 4 sides, we only had 2 legs on opposing sides. So adding the other 4 legs greatly increased our factor of safety so that our design would not fail.
So similar to the motor torque calculations we have in our controller subsystem analysis, we are assuming another reset that will take 600 seconds at the end of each day, starting from rest. In this case, this is for the 2 gears shown in the upper right corner. The smaller gear is driven by the motor, and the outer gear is what is rotating the rest of the heliostat module. So note that the gear ratio between the 2 gears is 1/3, and assuming that the reset for conservative purposes is 1 full rotation of that outer gear, we found the angular velocity and accelerations of the outer gear, and then using the gear ratio of 1/3, we found the angular velocity and accelerations of the inner gear, which is the driving gear. And then through SolidWorks, we found the moment of inertia for all of the parts that are being rotated, and that got us a motor torque of 4.2 times 10 to the -4th Newton meters. And we use that for our power calculation. So the minimum power to move this motor during our reset is 1.32 times 10 to the -2 watts. And moving away from our analyses, we have our cost. So this is our cost per square meter for an entire heliostat field. As you can see, most of our cost comes from manufacturing. Almost half of our manufacturing cost is actually from water jetting. So we have a few parts that need to be water jetted. The gear you saw in the last slide, the outer gear, those teeth are being water jetted, as well as our connecting rod, those teeth. And there's also some internal cutouts from parts such as our sheet metal backing and our heliostat base. Those also will need to be water jetted. And another chunk of our manufacturing costs actually comes from removing the coating from our galvanized steel sheet metal so that we can weld our parts together. Moving on to assembly. Sorry, can you go back? Moving on to assembly, we found that the wage of an assembler, including benefits and other expenses, is $55 per hour. And our total assembly time for our design is approximately 40 minutes. So that's where we got our cost from. Our raw materials are mostly from buying sheet metal, and our off-the-shelf parts are mostly from our motors and our spur gears. And lastly, for energy, the only machining operation that used a substantial enough amount of energy was our injection molding of our plastic parts. So we used those calculations along with GRU's prices for electrical power to get the price of 2 cents. And so we have a total of approximately $500 for the entire heliostat field. I know the cost is a lot, but if you go to the next slide, Marcus. So the cost is pretty high, but we do have our design's lifespan to be predicted well over 20 years. So there's that. So we have brushless DC motors, which have an estimated lifespan of 10,000 hours. Through some calculations with how often we'll be using them, in ideal conditions, our motors will last up to 68.5 years. However, obviously, given wind conditions and any other factors, we would assume a pretty conservative amount is 40 years of lifespan, which is still double the customer needs. Additionally, we're using borosilicate glass, which is highly resistant to thermal stresses, so it will have a much longer lifespan than any typical glass. And lastly, our design is made mostly from sheet metal parts that are designed for infinite life, as shown in our calculations. And just to point out, there's also been an increase in prices lately and inflation, so that definitely has an effect on our total costs of our heliostat design. So just to highlight some key features, our design is modular. For example, we have mirror clips that make it easy to remove and reattach mirrors in case of maintenance reasons. Our design is durable and easily manufactured. Most of it's made from the same type of sheet metal, so that makes it easier on everyone. It's easily installed simply by pouring concrete into the ground, and there is minimal actuation required because our connecting rod makes it possible to rotate four of our mirrors with the use of only one motor. So to quickly summarize everything up, Operation Concentration has designed a product that is easy to manufacture due to its simple materials and techniques. It's quickly installed on the site of the solar farm. It has a lower cost than most heliostats on the market today, and it is a modular design to allow for faster maintenance. That is it. So thank you to the UF Department of Mechanical Engineering, and thank you to our corporate sponsors. Any questions?
Okay, I would like Julia to go first.
Yeah, you would. Go back to the cost slide, please. So this you're saying is, because I believe the customer requirement was $100 per meter squared, right? Is this saying that this is $504 per meter squared? Or?
Yes.
Yeah, okay. So if I was an investor, like truly, I would have already signed off this meeting. To be 100% honest, how did you determine the priority of the customer needs? I know they gave a lot to you, so you were going to have to prioritize at some point. So how did you go back and say, okay, this need is more important than that need?
We kind of did that in our trade studies, I would think, where we
Mhm.
rated which ones were more important than others, just to get, when we were doing our decision matrices, we got our weightings of all of our different
Okay, so did anybody actually send an email to ask the professors to ask the customer where they could have wiggle room in their customer needs?
not that I know of.
No. Okay, so if just on a random, in the real world, customers will give you everything they want, right? Like if I'm going to go to somebody and I'm going to buy a heliostat, I'm going to literally give them like my pie in the sky wish list. And that's what we're going to call the customer needs, right? Your job is to then go back to the customer and one, get real crystal clear on what they actually want. Because lots of times the customer doesn't actually know what they want. So let's say they give you 10 needs, you go back with 20 questions. Okay. Do never, never, never be scared to go back and ask questions, because like I said, usually I've never dealt with a customer in producing customer needs that we've never gone back and actually adjusted what they wanted. Okay. Because again, usually we customers are not always that smart. Okay. Take that whole customer is always right thing and throw it straight out the window, because usually we customers don't know what we're actually saying. So please always go back and clarify. So here's my problem here, right? Y'all prioritized the money to the very bottom, essentially. If I'm an investor, I may only have $100 per square meter. So I really like this thing, but I literally, my hands are tied. You know, I do not physically have the funds. Or maybe I can go back to my boss and be like, okay, so they needed $160 per square meter, not 100. I know that's more, blah, blah, blah. But there's no way on this green earth that I am risking my job with my boss to go back and ask for 5 times the amount. So, I understand that's not that. This is the part that everybody hates, right? Even in the business world, we hate costs. We do. I understand it. Believe me. But part of the job is trying to figure out how to make these less. And the problem is, I'm not an engineer by any stretch of the imagination. I don't know a thingamajig from a what's-a-bob. Okay. So I can't tell you, oh, well, what about you go back and do this and that may reduce your cost, right? So I can just tell you, overall presentation was great. Like I said at the beginning, I love the fact that y'all have matching backgrounds. I love the fact that you're dressed up. It gives me faith in y'all, which is part of the reason I didn't just sign out, because I've got a meeting in 7 minutes that I should be preparing for. And especially when I saw the cost of $500, I was like, you know, done. But the fact that you guys look like you have your act together, you presenting like you have your act together, and you did acknowledge, hey, we know we didn't hit this target. That actually speaks volumes when you acknowledge it. Some people just kind of try to hide it. Okay. If you try to hide it and then I find it, oh, buddy, that's even worse. That's like, I have a 2-month-old puppy. When she tries to use the restroom in the house and hide it, if I find it, it's a lot worse than if she just did it and admitted it. So yeah, I don't know what else to tell you other than you got to fix those costs. But again, thank you very much for looking professional, because again, that's part of the reason I stayed on the presentation, is because I was like, okay, they got some work to do, but I have confidence that y'all can do it, because at least you look like you have your act together. Whether you do or don't, I don't care. That, you know, that's your thing, but you look like you have your act together. So my 2 things is get those costs down, and always, because you kept in the presentation, you said the customer need we saw as most important was this. You always got to go back and ask the customer what they think. Never assume. If, assume makes a blank out of you and me. Okay. So never assume, especially for me as the customer, maybe this was my number one customer need. Maybe my number one customer need was under $100. I'm like, okay, I can deal with less axles or thingamajigs or who's and what's it. Okay. So always go back and get clarification and ask questions. We know you're probably not going to hit, our grand wish list, but at the same time, we're not going to tell you unless you ask what we really want. Questions are good. Questions are always good. But like I said, I'm not real good with the Oreo, the good, bad, good thing. So I'm not even going to try that. But again, y'all at least looking like you have your act together gives me faith that it gives me confidence that I can give you this feedback to go fix this and that y'all actually would be able to. Okay. There's sometimes I've given feedbacks to groups and I'm like, they don't care. They're not listening. They, could give a flying flip. But by looking professional, I feel like y'all are taking this seriously and you would go back and fix it. And like I said, I have another meeting in 5 minutes that I'm actually supposed to be preparing for. So great presentation, really good job. Fix those costs, get customer needs. Have a great day, people.
Thank you.
Thank you so much.
Thank you, Julia. And I would like to thank Rick Miles for showing up and ask him to go next if he has any questions or feedback. Rick, are you there? I'm asking him to unmute. Well, while we're waiting for him to get back to us, yeah, I have a bunch of stuff typed out. So I definitely think this group did a very thorough job, down to everything, to making sure you had all the limit switches you needed, you had all the drivers you needed. There absolutely was nothing missing from your design. And in terms of the price, so there was a source. When the customer came to us, they said they felt they could get heliostats for $100 per square meter. Now, granted, that was before, originally it was before the supply chain issues with the COVID issues, and then it was definitely before the Russia-Ukraine dust up. And I know prices have gone up, but do you have a source for what other commercial heliostats cost per square meter currently?
Yeah,
Is
we
that-
did. One,
That intrigued me.
I can pull it up real quickly.
Yeah, and I don't want you to, take all this feedback and rework everything before the final project due today. That would be stupid. But if you do have any commercial sources, that might be a great thing to throw in your report. It's so painful that it hurts so much because I know your engineering work was so good. I would say if one thing I think drove the cost up too high, it was probably the mirror. So you start with the reflective surface and it drives everything else. So you use sheet metal to make sure that your mirror was stiff, even though you were using glass, which is, fairly stiff. And I'm thinking, maybe if you could, if you had to work on this for another semester, that maybe starting with that and trying to get a lightweight, cheap, stiff backing, like maybe Mylar film on plastic or something, then that would cascade down everything. You wouldn't need as big a stiff a structure to handle that weight. You wouldn't need as powerful motors, and everything could scale down after that. So if I had to go back, where in the design tree caused the cost to just blow up, I would say probably, right at the surface. And, sometimes you think you need something and you make a decision and it just cascades and sends you irrecoverably to the cost overruns. I definitely feel like any project I had with sheet metal, I would hire this group to design a cost-effective sheet metal product where you're reusing the cutouts and know how to get a stiff structure from a thin sheet of sheet metal, which unfortunately in the past 3 weeks, the price of that has skyrocketed. So way back when you made your first design decision, you had no idea what was going to happen to the price of sheet metal and the price of aluminum. So these things, that's an engineer's life. I would like to thank you very much for being honest about it. Like Julia says, don't try to hide it. Just say, this is beyond our goals. We did not meet our goals on this, and we would like to do better. Let's see what else. Rick, are you there yet? Okay. So,
I am, Carol. So sorry, I got a phone call that I had to take that I was waiting on. But I was able to watch a lot of the presentation, so I did have a couple of comments to pass along. I really enjoyed the analysis that was done. Loved the fact that the team did free bodies. I thought the rack and pinion with the Lazy Susan was a nice, unique design concept that I had not seen before. So I really thought that that was really good. I think I've heard y'all talking about the cost, right? And I'm sure Julia touched on that. One of those things is how you get closer to that $100 target, but the overall concept and the thought here, I just love that it was different than what I'd seen from other groups, and it was a different approach on things. And I kind of agree with Carol that using the galvanized steel and stuff, looking at ways to drive down some of that cost, and usually it would be towards the low end is a good way to think about this thing. So I really thought you guys did a really good job of, again, there was a little segment of the presentation I missed towards the end. I was glancing at the slides, but I couldn't hear you talking. But the part that I heard, I thought y'all did a really excellent job in presenting your material.
Thank you very much.
Thank you.
and I can see we've sort of run over a little bit. And there's the standard feedback line for everything and every project is there's room for improvement, but today's the due date. There's not certainly time to go back and redo your whole project, and when the price of raw materials doubles in the last 3 weeks of your project, there's not a whole lot to adapt for that, other than in your final conclusion. You can relate what kept you from meeting your needs, and I say alternatives for future research would be using whatever you think, just a little something. But the engineering calculations and the engineering work behind making sure all your other needs met were excellent. It's just sometimes in that decision tree, some little fork in the road takes you way off course on something like the price. And unfortunately, that's what happened here. But like Rick Miles said, there was a lot to appreciate about this design, and I absolutely would recommend this group to work on other mechanical designs, especially that might need to heavily rely on sheet metal, because you really seem to have a good feel for what all you can do with a very thin sheet of metal. It's just twice as expensive as it was 3 weeks ago. So I'm going to stop recording